Okay, so new topic for today. We're going to talk about this idea called change of variables. This is a really powerful technique for doing integrals. Really powerful. Y'all may have noticed that sometimes doing a triple integral or a double integral is a huge pain. Right? Thinking about how to slice it up, and sometimes the shape is just not very well suited for slicing. And it's a real problem. And change of variables is going to help us with that. It's going to take us a while to see how exactly, but bear with me. Okay, so I want to start off with an observation. Y'all remember when we defined single variable integrals? I say we, when y'all in your single variable calculus classes define integrals. In practically all cases, they make this definition with delta x's all being the same. I want to point out, you don't really technically have to do that, right? I mean, let's suppose that you defined integrals this way, where the different delta x's are different, right? So what? Right, from a certain point of view? Depends on what you're calculating, I suppose, maybe, and the circumstances, but if you were to slice it up irregularly, let's suppose you're computing the area under a curve, you're still going to get a bunch of little slivers of area, and it's still going to add up to the total area, and what's the problem? Right? If you're computing the mass that's distributed along this interval, well, the total mass is still the sum of the little pieces of mass. It doesn't really matter. Now, a reasonable objection you might make is, yeah, but why would you ever want to do such a thing? It's clearly more convenient, right? So let's make it all a nice simple formula, b minus a over n. Why would you want to deal with the fact that these are different? And how are you going to even write down what they are if they're not all the same? Fair point, right? I'm not suggesting that we actually do this, right? But I'm just pointing out if, for whatever reason, we end up chopping up an interval irregularly, that's okay. That's my first observation. Okay. All right. Now let me remind you of the substitution rule, another seemingly irrelevant point. Flashback to old single variable calculus stuff. I hope you all remember the substitution rule. You may remember it as simply sort of a convention that if you have one variable being a function of another variable, then you can just do this and it's sort of okay. Right? That's kind of the way students tend to think about it in Calc 1 classes. Calc 2, Calc 1, Calc somewhere along there. But here's how you write it down as a rule, and you may have seen it written down as a rule. And now you also may recall that the bounds for the x integral are not the same as the bounds for the resulting u integral, or whichever way it goes. Right? Okay. Now why is that? Well, it's pretty clear if you think about this from the point of view of the fundamental theorem of calculus, these values here are values of x. Right? And if x takes a certain value, well, then u takes a different value. Right? If x is equal to b, plug that into the given formula, that means that u is equal to g of b. So, I mean, again, if you do the antiderivatives and plug in, this is kind of what you have to do to not get nonsense. Right? This is just what makes it work. Point of view. Okay. All right. I want to take a different point of view on where this comes from. The purpose of the different point of view that I'm going to take, y'all remember I do this a lot, right? The purpose of taking the different point of view in the single variable context is to take a point of view that's going to generalize nicely to the multivariable context. And that's what's going to happen here. So, new point of view on where this comes from. Let's explicitly write down what we mean by saying u is a function of x. So, here you go. There's your function, g. X's are the inputs. U's are the outputs. Okay. Okay, so, this applies to, for example, a. There's a, and if you plug that into this function g, then out comes g of a. There's no surprise there. That's clear. Likewise for b. Likewise for all the points in between, as long as this is a sufficiently nice function. And so you might say that this interval goes into the function and out comes that interval. That's a point of view you might take. All right. Now, seeing this g function a little bit more explicitly, a little bit more geometrically. Keep in mind, up here it was just an algebraic kind of an algebraic hack almost to make integrands work out nicer or something. Here we're explicitly seeing it as a function. And now let me make a modest observation that, well, if I have such a function, if I were to take this interval from a to b, and if I were to chop it up into little pieces, well, I can take these points individually, like this point here, x1, I can plug it into g, and out comes some value, g of x1. Likewise for all those other little endpoints, right? For x2, x3, x4, you can chop up the whole thing, plug all those new chop points into g, and you get effectively then a chopping up of this interval on the u-axis. Now, the annoying, awkward thing you might say is, well, yeah, but this is, we were very careful to do a regular partition here because we like regular partitions, and this g function's not necessarily linear. It could be all sorts of weird, and it's entirely possible that this partition here then is not a regular partition. And so now maybe you're starting to see why I made this observation up here that, yeah, well, who cares? Doesn't really matter. Whatever. How are we doing so far? Now, where I'm going with this and exactly why we care yet to be revealed. But is everybody on board with the setup that I'm creating? Yeah.
So do we also assume that in the irregular partition, every piece is still infinitely small?
Oh, no. We're not. No, there's no such thing as infinitesimals. We're not talking about it. No, these are finite pieces. Finite, absolutely finite. Yeah. Right. So let me remind y'all. Infinitesimals is one of the rampant misunderstandings that exists in single variable calculus classes about what is a single variable integral. And so if you're not entirely clear on that, this would be a great opportunity to go back to remember I made a recording about integrals on my YouTube channel in the miscellaneous topics playlist. That'd be a good one to take a look at. It's several other common misunderstandings that I addressed there. But yeah, there's no such thing as infinitesimals among the real numbers. Okay, right. So here we go. So how big are these pieces? Some of them are bigger, some of them are smaller. So how big are they? I mean, these are all conveniently the nice same size. These are all b minus a over n, and that's not what we have here. Sorry. So we do have a chair here. Go. Yeah. Okay. All right. And there's a spot over there. Yeah. Okay. Cool. Excuse me. So, how big are these pieces? They're not all the same. I need to know how big they are, and conveniently, we have a tool for figuring out how big pieces are. And that is the derivative. I mean, we haven't thought of the derivative in such a way, but nevertheless, it works. If I have a little piece here, from x sub I minus 1 to x sub I, that little piece of size delta x, I can think of that delta x as being a size, but let me remind you, I can also instead think of it as a change. I can think of it as in how much the variable x changes as I move across that piece. And changes to the input of a function, and then the resulting change to the output of the function. And of course, now make the observation that output change, that's the size of the output piece. Right? Thinking of them as changes, we know that the relationship between input changes and output changes is the derivative. Right? This input change, delta xi, this output change, delta ui, it's the derivative, specifically the derivative of this function that tells us the factor relationship between those. So, flashback to chapter 13. Hope everybody remembers that. Okay. Everybody on board so far? Again, why we care and where we're going with this, and how does this help me compute multivariable integrals? Coming up soon. Okay. All right. Okay. So, with this layout all set up, what I want to do is look at our image interval over here. And on that image interval, I want to ask the question, how would I compute an integral? Let's say like this. Now, why I would want to do such a thing, you'll see why in just a moment. But for whatever reason, let's compute an integral. Let's write down an integral on this interval of the u-axis. And, of course, it's a Riemann sum, right? The way I do integrals is a Riemann sum. No problem. Plugging in, definition of an integral. And then just notice everything in this expression here, everything in there, I can rewrite in terms of x's, right? So specifically, I mean, where did these ui's come from? You know, these points in a given interval. Points are okay. Values of u are just g of the corresponding values of x. Right? So I just plug that in. Notice I've rewritten what had been written in terms of u. I've now rewritten it in terms of x. Likewise, what is this delta u? You know, how big? What's the size of that little piece of the domain? Well, it's a formula from the previous page. Delta u there's a formula, all in terms of x. So just plug it in. I've now taken everything that was written in terms of u and rewritten it in terms of x. Okay, now, again, why do we care? What's the point? Keep in mind we started with an integral on the u-axis for no particular reason. We wrote that integral as a Riemann sum. We have now rewritten that Riemann sum of u as a different Riemann sum. And notice that now everything's in terms of x, and even though it came to us as that times that, I can move parentheses around just a little bit, and now let's rewrite it as, a Riemann. Let's just move parentheses around like that. There you go. And now what I've got is a brand new Riemann sum representing, in fact, an integral, and you can write out exactly what this integral is, and it's, come on, sometimes my stylus, just right at that dramatic moment. There you go. That new Riemann sum is that integral. Okay. All right. And notice, this is exactly the substitution rule that we wrote down previously. So this is, like I say, a different point of view on where the substitution rule comes from Calc 1. Okay. Pause for questions. How are we doing? Yep.
So how do we explain the bound change?
Oh yeah, so the bound is an immediate consequence of what the Riemann sum says. So this summation is a summation as I goes from 1 to n. Therefore, this is a summation as I goes from 1 to n. And if you just look at these values, right? Look at these values here. What are these xi stars? Well, there's an x1 and an x2, and those values just move right along there from x0 to xn. Yeah. Does that make sense? Yeah. A to B, in other words. Okay. Right. Yes?
Why did we go from the u integral to the x integral?
Yeah, I know. It's weird, isn't it? It's seemingly backwards. Doesn't it seem backwards?
Yeah.
I'm going to get to that.
Okay.
It's a great question. Yeah. Okay, so in fact, let me get to that sort of right now. So we call this this act of plugging in, we call that a pullback through the g function. I say pullback. This is a common term. I did not make this up, by the way. I call it pullback, though, because g is going forward, and yet the expression seems to have gone backwards. Right? The function pushes that way, but the expression then, as a result, just pulls back the other way. And if you think about it, that's just how plugging in works. Right? You don't have to do something complicated with integrals and differentials and stuff like that in order to see this phenomenon. If you had some expression over here like, I don't know, u squared plus 5u, that's an expression on the right. And if you plug in u equals g of x, that would then turn into an expression over there on the left. And so it's a short answer. That's just how plugging in works. Yeah, and it seems weird and backwardsy, but it's life. Is that satisfying?
Yeah.
Okay. Anybody else? Feel free. Okay. Right. Okay, so be aware of this term pullback. This is a lovely construction. We're going to be talking about pulling back different kinds of integrals at different points in the course. But so again, this is the nature of the pullback because the function g goes the other way. Okay. All right. I also want to introduce another little term here, and that is the factor here, g prime. The factor that I multiply by delta x to get delta u. I like to call that a stretching factor. And it's pretty natural to motivate. I mean, look at that little interval on the x-axis over there, that green interval. It was this big, and then in the process, what does g do to that interval itself? That interval of size delta x, by virtue of what g does to it, it gets stretched out. I mean, it's literally a stretching that happens because it was that size and now it's this size. And this is the factor by which it got stretched. Its previously smaller size became a now larger size. That's a stretch. Okay, so what I'm going to say here is that in this sort of a substitution, what we call our substitution rule, the stretching factor is g prime. And by stretching factor, I just mean that when you're looking at sizes, how do sizes change? What do you multiply by in that size change? Okay, so heads up about these two terms: stretching factor and pullback are going to come up again and again as we go through the rest of the course. Okay, all right. So here's what we're going to do now. Back to multivariable calculus. We're going to consider, can we do something kind of sort of analogous? Obviously not exactly the same, because we're going to change the context. We're going to look in a two-dimensional context. But can we do something that's morally equivalent with the understanding that it's in a different dimension for double integrals? Okay. Look, the ideas are largely the same. Let's suppose now instead of an interval, suppose I'm looking at a rectangle. That's sort of a two-dimensional analog, right? I can talk about how to slice up a rectangle. And you could imagine that having a sliced up rectangle, I could then take a function. And I could plug in everything into that function, and out would come, not a rectangle probably. I mean, this is going to be, who knows what kind of function that function g is. It might be wacky, some weird way. And likewise, those slices, each slice, each slice is made up of just a bunch of points. Points go into the function. Those slices, when they come out, might something like that. And it's hard to do this on the fly, but maybe those slices would end up looking kind of like that. And as a result, little pieces of the domain, such as that little piece of our original rectangular area, that little piece is going to turn into something sort of like that. And now I'm going to make a geometric appeal, and I want to prove this, and let's not get into the weeds on this, but this rectangle was made up of slices that were kind of near each other. These are straight lines, and then even though on the whole their images are going to be curved, at least sort of locally, they're going to look approximately straight. No, not exactly straight, but they're approximately straight. And then likewise, they're also going to be approximately parallel over here. These aren't going to be exactly parallel, but pretty close. And so then likewise, these pieces here, their images are going to be approximately straight and approximately parallel. So the image is going to be approximately a little parallelogram. Not exactly. It's going to be a slightly tweaked, slightly distorted, but nevertheless approximately parallelogram. Okay. Right. So we're going to try to do the pullback strategy now. I'm going to try to consider the question of, suppose I have an integral defined on this domain. Remember, that's where we started up here. We started with an integral defined on the right, an integral sort of in the output world, and we then did a pullback to turn that into an integral on the left side, into the input world, if you will. So I'm going to try to do the same thing. And you'd be surprised, there's not that much to it. It's kind of the same idea. X comma y. What is x comma y? Well, x comma y is some point over here. It's the coordinates x and y. Those are the outputs that come from this g function. Right? It's the outputs that come from this point u comma v. So uv is related to xy by way of g. So for color coding, x comma y is just g of u comma v. Now just plug it in. Like again, now of course plugging in tends to pull things backwards. So what had been a simply written down expression x comma y now gets turned into this different expression g of u comma v. Then there's the issue of size, and here's where I'm going to have to sweep something under the rug. We'll come back to it at a later date. But this size here, dA, the area in the xy plane, when we write the integral, we'll eventually write as dx dy. How much area is that in the xy plane? That little piece of area, it's not the same as this little piece of area here, du dv. They're not the same. They're very much not the same. That little rectangle gets stretched out. There is a stretching factor, right? That stretching factor is what you multiply by the green area to get the blue area. And what's the formula for that stretching factor? Well, it's not immediately obvious. We had this. We were very lucky back here in this single variable context. Oh my God, look at this. Sizes are changes, and we know how to relate changes. The derivative. It fell in our lap in the single variable context. So not so here. So what I'm going to do, I'm just going to tell you what it is for the moment, and we will talk later about why that is. But this stretching factor, it is the absolute value of the determinant of the Jacobian matrix that we talked about back in chapter 13. And there's great reasons for this, and again, we'll talk about why later on. So just make sure to know this formula. It's the absolute value of the determinant of the Jacobian. Okay. Now, before I go on to the a little bit lower down, I do want to talk about a notational convenience. I think this is a fantastic notational convenience. I'm a big fan. It is commonly written that instead of determinant of the Jacobian, you write partial xy, partial uv. And here's kind of why. There's a couple different points of view on it. But it's pretty natural, really. If you remind yourself, what is this Jacobian matrix? Well, there's the Jacobian matrix. The determinant, then, of the Jacobian matrix, that's that formula, no big deal. And notice, what we have is a bunch of partial derivatives. We have a bunch of partial derivatives of x and y, bunch of partials of x's and y's in different places. And they're all partials with respect to u's and v's. Right, so it's kind of, if you were to say, in reference to this Jacobian here, if you were to say the partials of x's and y's with respect to u's and v's and organize it in a natural fashion, then it's kind of right? And this notation that I have over here on the right, it's kind of suggestive of that point of view. Right, so that's one point of view on it. The other reason, really more of the reason that I'm a big fan of this, is that if you take this point of view on the stretching factor, if you rewrite the stretching factor like this, then notice this formula for the stretching factor, partial xy, partial uv, dA, of course, is du dv when it's over there in the UV plane. And what that turns into then, of course, is dx dy over here in the in the xy plane. Notice what happens. What we really have then is, let's get it all to fit. Oh, didn't quite fit. No worries. Okay, so here we go. It's as if the du dv and the little partial u partial v, it's as if those kind of cancel. And then the kind of sort of leaves dx dy kind of sort of, at least notationally suggestive, over there as on the right as a leftover. Now, this is wildly inappropriate nonsense. This is not a fraction. Right? I'm not saying it's a fraction. I mean, look at it. Look, what is this thing? It's a determinant, for crying out loud. It's not a fraction. There is no actual cancellation here. That's a lie. But it's awful convenient. And it's very satisfying in a way, you know what I'm saying? So, this is a notational convenience that I like and I encourage. Just don't be under the illusion that it's something that it isn't. Right? Don't overinterpret it. Right? But nevertheless, it makes me like this notation. Everybody on board? Okay. All right. Okay. So, now a word of warning about the book. The book makes a notational choice that I find uncomfortable. The book takes this stretching factor. Here's 3 different ways that you can write the stretching factor. The book refers to that stretching factor as just JG. I don't like that. I don't like it because that matrix by itself is what I call JG. To me, that's the Jacobian. J for Jacobian. Now, we need that matrix. I mean, think back to chapter 13. In chapter 13, it is the matrix itself that you multiply by input vectors to get output vectors. We weren't taking any determinants back in chapter 13, right? So I think this, what I call the Jacobian, should be the matrix. The book refers to the Jacobian as the determinant of the matrix. So, uncomfortable, awkward, my apologies. If I encourage you to write it my way, because I think it makes more sense. If you're concerned about deviating from the book's conventions, okay. No one that sees you write this down is going to not know what you're talking about here, ever. It's not going to happen. So I think I think this is the safe notation, and I would encourage you to ignore the book's notation. Okay. All right. Now, so we've done a bunch of stuff. Let's get back now to the question of why are we doing this and who cares, right? We started off talking about different ways to think about integrals, different way to think about the substitution rule, right? I mean, who cares if we have a different point of view on the substitution rule? I guess you can kind of do the same thing for double integrals, but so what? Why are we doing it? Here's the big reveal why we're doing it. If you find yourself looking at an integral on a domain like that, for crying out loud, stylus. Doing an integral on a domain like this, you might just very well wish that you could turn that integral into a different integral with a different domain that is a nice, pretty rectangle. Because think about the brute force approach. How would you slice up this domain over here? Well, oh gosh, you'd start off maybe slicing like that, and you'd get a bunch of pieces, but then you're going to slice through that corner down there, and then you slice just a little bit further, and now something weird happens when you sideswipe that edge, and then you're going to slice through that corner, and then you finally finish it up there. You've got to have 4 separate pieces. A straight up brute force, plow forward approach to integrating on this domain has 4 chunks. And that's a bummer. Highly undesirable. Nobody wants to do that. So the big win, huge win on this is that we can rewrite this integral on this domain, this mega bummer. We can rewrite it as a different integral on this nice, pretty pullback domain. As I have it drawn here is even a rectangle. Isn't that lovely? It makes your life a lot simpler. So that's the big point, right? And I think it's interesting to notice how different this is from the motivation for the substitution rule. So here you go. Here's the substitution rule. Why did we do the substitution rule back in Calc 1? But was it that we were so upset about what the bounds were? No, of course not. Never. Bounds are the numbers you plug in at the end. It's the easiest thing. It's the easiest part to deal with integrals. Was plugging in the bounds, right? That wasn't our motivation. Our motivation in Calc 1 context, Calc 2, was that maybe this integrand was bad, and I wanted to turn it into a different integrand. And that was awful handy. We just find ourselves with totally different motivation here. Here, our problem isn't necessarily the integrand. I don't know, maybe it is. But the problem here is the domain itself. It's a real tricky idea. Okay, let's see some examples. Let's get our hands dirty. By the way, in these examples, I'm going to kind of build up to harder and harder examples. I'm going to start off with a marshmallow, a freebie. I'll point out what's part of the marshmallow aspect of this example as I go through it. But let's suppose I'm interested in doing an integral on this domain. That domain R, being an image, given as an image of the unit square in the UV plane, specifically image by way of this function G. So there's the phrasing of the problem. Notice, though, I'm interested in doing an integral over an ugly domain, and I don't think I have to give you a very strong sales pitch to try to persuade you that this is an ugly domain, right? You're going to slice through corners, and either way you go, vertically or horizontally, this is 3 separate, right? I mean, nobody wants to do that. Okay. Marshmallow aspect to this problem. It is explicitly given, right? Our undesirable domain is given to be an image of a nicer domain. We are given what that nicer domain is, and furthermore, we are given what the function is, whose image is that which we are starting with, right? So there's, again, I don't want to talk about, how do you figure out what the pullback domain is? How do you decide what your change of variables function is? Well, there's different situations, different examples, and we'll talk about those as we go on. And again, I don't want to deal with that for the moment. I want to get our hands into the mechanics of how you apply the change of variables method, right? So we're going to take that G, we're going to say, thank you very much, I'm glad that's given, and we'll worry about how to deal with other circumstances later. Okay. So, formula. The pullback is going to do this. In order to write that down, I'm going to need to know what the stretching factor is. Here's my formula for the stretching factor. The stretching factor is what we sometimes call the Jacobian determinant. So the determinant of the Jacobian matrix. It's a little bit easier to say Jacobian determinant. So, compute. And here we go. A couple of partial derivatives, right? First, taking the partials with respect to u. There's the u partials of x and y, right? Taking the partials with respect to v. You see those? So there's your Jacobian matrix. Oh, look at me. I forgot. Oh, shame on me. Look at that. I forgot to write determinant here. Sorry about that. So taking that determinant, that times that, minus that times that, and there's your stretching factor. Let's see, yellow. Our stretching factor is this expression right here. And has absolute values in it. This is an awkwardness. Students very often, I don't know, I think a lot of students have been sort of conditioned to get away with little absolute value crimes from high school. When I'm in my high school, if you were to just kind of ignore absolute values, he might count off a point. Whatever. Yeah, okay, well, stop you one point there. But students were never really forced into really thinking about that. And that's not appropriate, right? I mean, the absolute values here are important. And so let's think through now, what do we do with these absolute values? How do I know if 4uv minus 9 is positive or negative? Or is it sometimes positive, sometimes negative? How do I deal with this? The way to deal with this is actually looking at us on the page right now, because you can see explicitly what u is. See, there's the u-axis, and you can see in my pullback domain, u is always between 0 and 1. It's right there. Right? You can likewise see what v is. That v right there, here's the v-axis, and you can see v is always between 0 and 1. And now let's just look at this expression, 4uv minus 9. If u and v are always between 0 and 1, then I've got something that's always between 0 and 4, and I'm subtracting 9 from it, and that's always going to be negative. Everybody on board? So it's something that's important to deal with, but usually is easy to deal with. So just make sure to deal with it. Okay. Right. Okay. And as you all know, of course, the absolute value of a number that's always negative is its negative. Yeah, think that through. Okay. Right. Okay, so now it's just a matter of plugging in. It's pretty much all over. There's our stretching factor. If we want to know, area on the right-hand side, well, it's stretching factor times area on the left-hand side. That's stretching factor right here, 9 minus 4uv. Right. There's that. And now I just have to deal with the domain. Here's a very common mistake that students make, super common. This is wildly inappropriate. But another thing that I guess students have been sort of conditioned, unpenalized in high school context. I don't know. But you can't just say, well, I guess X is U now. I guess Y is V, I guess. I don't know. Right? So lots of students will just kind of scratch off the X and put U, scratch off the Y and put V. That makes no sense at all. It's absolutely inappropriate to what we're doing. And notice in our formula here, in our formula here, it tells you exactly where X and Y come from. X and Y are G of U and V. That G function will tell you how to get your X and Y. And in this example, you can explicitly see it. That X right there it is. It's U squared plus 3V. It's in the change of variables functions right there, staring at you. Right? So that X, U squared plus 3V from there. Likewise, this Y, there it is. It's V squared plus 3U. There it is. Everybody on board? Now you might look at this, at a glance. Let's look down at the algebra at the bottom of the page here, and let's try to decide: was this worth our effort? Was this a win or a loss? And there's a temptation to look and say, "Oh my gosh, this is a big loss," because that nice, pretty little integrand right there turned into this great big integrand here. And well, golly, I like smaller better than bigger when it comes to integrands. Right? But that's not the point. It's really not the point. And this, I guess it's a little bigger, but it's still a polynomial. It's just not that bad, right? It's nothing to be afraid of. The big win is in the domains. This monster domain has turned into the unit square. Constant bounds, zeros and ones, right? So what would have been a super ugly trio of iterated integrals is now one easy iterated integral instead. Everybody happy? Okay. All right. Okay, here's another example. In this case, I'm not going to give you the change of variables function. Okay, so we're going to have to figure out the change of variables functions kind of, sort of, anyway, on our own. This is the case often, that the change of variables function is not given, and you got to kind of make a reasonable choice, figure out, how to find it. Something like this, where the domain was really ugly, it would be pretty hard for me to give you this domain without telling you sort of, or at least giving you some sort of strong information about what that change of variables function is. But very often that's just not true. Let's look at this case here. Here my domain here, R, is this square with certain corners given. The corners being there, 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 there. So our square, our domain is that. Right? And not hard to see how to think of this square as being an image of something nice. I mean, details aside, this is what you get when you make a rotation. This is what you get when you make a rotation of that square. And I just appeal to your sense of geometry. If you take a yellow square, and if you rotate counterclockwise by an angle to be determined momentarily, take an angled square, a non-angled square, rotate it, it becomes the angled square. It is pretty clear right away how this ugly-looking domain is actually an image of something. It's an image of a counterclockwise rotation. Okay. A couple of details to worry about. What is the angle by which I'm rotating? This angle. You can determine it by noticing that point is this point, and you've got a little familiar triangle right there to look at. This is the right triangle. It's 30, 60, 90. Flashbacks to high school geometry. That angle's pi over 6. Okay. How do you do a rotation? What is the formula for a rotation? Well, you'll notice that is actually given in the question, and this, we hadn't covered this previously, so just, sort of fair, I think reasonable is, in general, if you would like to do a rotation by some angle theta, there is a formula that will do it. That formula takes anything in R2 and rotates by whatever that angle theta is. It's a handy little formula. By the way, if you take Math 216, I'll show you why that formula is true. It's not that hard, ultimately. It requires some tools that we don't have at our disposal here in this class. But anyway, we'll talk about that in the next course. So all of this given, we know what theta is, and we know how to do rotations. So I'm going to take this theta and plug it into there, and I can then write down exactly what the rotation is that I need. The rotation that I need to turn u comma v's into x comma y's is that formula, that t formula right there. How we doing? Cool? Okay. All right. There's a couple of little details that remain. I'm going to largely leave for y'all to work out on your own, but you do still have to, compute the Jacobian determinant. Not hard to do that calculation. That calculation reveals that the Jacobian determinant is 1. Let me encourage you and also dissuade you from a different point of view on that calculation, keeping in mind that the Jacobian determinant's an area stretching factor, and when I rotate, I don't change areas, right? I mean, nothing gets stretched when you do a rotation. So geometric intuition kind of tells us that the answer here should be 1, and I want y'all to digest that, okay, this is satisfying that we got this answer, right? But I want to dissuade you from that sort of an argument in the following sense, and that is that, the purpose of this class, think about an exam question that has this kind of thing on it. The purpose of such a question is to confirm that you know how to compute Jacobian determinants, among other things. But so on an exam, I want to see that. I want you to have the geometric intuition, but I want you to give me the algebra. Okay, yeah.
So for this example, you said we weren't given the change of variables function, but we were sort of given the skeleton of the function.
Yeah, totally. Yeah, that's right. Yeah, exactly. And if you're wondering, well, how in general am I going to do it when it's super hard? Well, when it's super hard, you're not going to do it. And there's other situations. I'm going to show you another example momentarily where there's another sort of tricky, clever argument that can be made to find a change of variables function. All right. So again, big win. This highly undesirable domain here turns into this much better domain there. Rectangular bounds, constants, right? Plug in, nothing to it. Okay. All right. Neat observation. Sometimes, instead of thinking of x and y as functions of u and v, sometimes you might want to go the other way. Now, I'll make the observation, there is nothing magic about letters of the alphabet and alphabetical order, right? And it's just as legitimate to think of u and v as functions of x and y instead of x and y as functions of u and v. If you're thinking of, now just to repeat what we've already done, if you're pushing this direction from uv's into xy's, if you're doing that sort of a pullback, then here's your stretching factor. Note the faux cancellation. Right? But if you were to instead, for whatever reason, want to think of u and v as functions of x and y, now there's the function through which you're going to do a pullback. There's what the stretching factor would look like. Again, notice the faux cancellation. Faux, emphasis on faux. Right? So I cannot emphasize enough, this is not a fraction. And this is not a fraction. But because it kind of behaves like a fraction in that sense, and also it sort of behaves like a fraction in that sense, notice that an immediate consequence of these two formulas, neither of which relies on thinking of that as a fraction, immediate consequence is this formula, which gives us another way in which that thing that is not a fraction actually kind of behaves like a fraction. Again, it's super convenient. Right? So, in fact, the fact that this thing behaves so much like a fraction is part of the reason that we like to write it as a fraction. So, yeah. Again, of course, it's not actually a fraction. Okay. The determinant. Okay, that in mind, this next example, this is a clever example. I wish I'd thought of this. But this got showed to me at a early age in my learning of the material. But suppose my domain is this domain here that is bounded by a certain four curves. These two curves here with those two equations, and then also these two curves here with these two equations, slightly different structure. So, four equations in the xy plane give me four curves that bound this region, and over that region is what I want to do my integral. And you might be thinking, okay, come on, how manufactured is that? When is this ever going to come up? What does it have to do with the real world? You're just being annoying, right? I want to point out where I kind of first saw this example, and it was in a physics class. It was a thermodynamics class, and I don't remember when that was. But anyways, if those of you who are engineers are probably going to have to take a thermodynamics class at some point. And if you want to do a calculation on the efficiency of a certain kind of an engine, it's called the Carnot engine. It's an abstract concept, but it's very important in thermodynamics. The calculation of the efficiency of the Carnot engine comes from an integral done on this domain. So it's not made up, right? These are very natural curves. The blue curves have to do with how do temperature and pressure relate under one set of conditions. And the purple curves had to do with how do temperature and pressure relate under a slightly different set of conditions. Yeah, interesting how that comes out. So this is not a manufactured example. This is a very real world. We're doing physics at this point in the process of thinking about this integral. And the big idea, and I see I've got seconds left. Oh, okay. Real quick, just so you sort of know where this is going. The real big idea here is to look at these first two curves and notice that they involve a certain expression being held constant, which I can then give a name. So I'm going to give the name u to these two functions x and y that are held constant, and I'm going to give the name v to these two functions xy squared that are held constant for those other curves. And if you use that to define your function, You define a function h like that, where now u and v are functions of x and y. Notice, it's really cool how this works out. This first curve, that super awkward curve, xy equals 6, well, that's now u equals 6. It's now a straight line. It's a real slick move, right? What had been an ugly curve, by way of this change of variables function, is now a straight line, and you can see that the rest of them are going to happen the same way. And so our new domain is going to be a rectangle. And details we'll talk about on Wednesday. Okay, all right. See you guys later. Oh, and I have homeworks to return if you'll stick around for just a moment.